So good afternoon, everyone. My name is Luca, and I'm here today to present my internship project that is based upon machine learning network attack detection. This is done through graph attention network, and this work is part of the Cyberus Master in Cybersecurity. And it's focused on leveraging this advanced technique for network anomaly detection. Today's presentation, it will be top-down. So we will first talk about the problem, then talk about the general architecture of the system, and we will go deep as we go. So we will build the system as we go, so to say. It's very important to say that this work has been done by me and Koi, and so one part is in this presentation and the other part is in his. I will of course present what I did, but for example the evaluation, that is a crucial part, it's part of Koi's presentation. Let's start. So, what is the problem? What we are trying to work in? Today, LAN, so local area networks, they are very complex and they are very filled with a lot of different kind of devices. For example, think about Alexa, think about the mobile phone, think about all the IoT devices, the computers, and as you know, there are a lot of threats that are targeting these, let's say, dummy devices. For example, when talking about botnets. And these kind of threats, they leverage, for example, 0 days flows that are hard to detect because most of the time, maybe for a couple of years, these flows, they are unreleased, so no one knows apart from hackers. And the problem is unsupervised anomaly detection. So we are trying to find these kind of malwares that are not known. So because as you can see, limitation of current approach is signature based, so it's when we already know what the threat is and we are trying to kind of stop it. Of course, it works very well for known threats, but it's polymorphic malware, so the malware can even change shape. The traffic is encrypted, so we don't really know what's happening. And so this problem we're trying to solve is to do an behavior-based solution. So where we have something that represents truly the state of the network, for example, a graph that is modeling the physical behavior of the network, and based upon the behavior of the nodes, the connection, we can try to see the behavior. So instead of looking for, it's like behavior with people, instead of looking for specific bad people, it's like we're trying to go for specific bad behavior, so to say. How did we do this? And sorry, one last point I forgot. Since we are talking about LANs, this project is supposed to work on router. So it's not for example, it's not like an antivirus you put on your machine, on your computer, or on your phone. It's something that is running on the router and is supposed to monitor a small network. So let's say between 20 and 50 devices. So how did we develop this? This is an open source proof of concept. And what is important is it's ready to run, it's ready to deploy. It's made up of 2 modules. So a C++ module that is a high efficiency optimized parsing mechanism. So this module is parsing Zik logs. Zik is a traffic analysis tool. So we are parsing these logs, building graph, and then there is a second component, a Python script where the real logic lies. So we have this graph attention network I will talk about, and this Python is it's parsing the graph from the C++ script, and it's analyzing, is doing some inference to kind of predict, to kind of try to reconstruct the traffic and see if it's malign or not. Of course, we will get into the details of how it works. This is the idea. What is of course, our inspiration, because this didn't come out of the magical hat. There are 3 key papers I inspired. One is called Hypervision, and from this paper I took the C++ idea of having a real high efficiency C++ script. So as you can see, it has a very high throughput. It says 80 gigabytes per second throughput, very important, because of course we are talking about live traffic. It's very similar in what it's trying to do, because this paper is trying to do unsupervised anomaly detection with the graph structure but we are doing it with deep learning, so with the graph neural network, and this paper is trying to use unsupervised machine learning. So it's more a statistical technique, and it can work well in some conditions. For example, when you're trying to work with specific kind of attacks, but it has some limitations. Anyways, it's a very nice framework, specifically for how it's coded. I took a lot of inspiration from that in C++. Then we have dynamic graph survey. Of course, all this is in the references of the paper. This is a comprehensive anomaly detection paper for graphs, and it talks about a lot of different methods, a lot of different kind of anomalies. You can see a classification here. It's a point, contextual, and collective anomalies, but there are a lot more classification based upon the type of graph. I will not focus on this, but it's very interesting. So, of course, I chose to use the graph neural network because, according to this paper, it's one of the best way to handle multimodal data. What does it mean, multimodal? For example, a graph models a network. You have some info about the network itself. So, for example, about the topological structure, like how many nodes, if a node is central or not, if there are a lot of incoming or outgoing connection. But then you also have some information about the devices themselves. So like IP address, number of packets, protocols used, if it's a server or a client. And all this information is called multimodal. So it's like multiple senses, like viewing, hearing, and touching. And what's crucial is to try to incorporate as many, not just feature, but kind of senses as we can in this machine learning. And so this is what I took from this paper. And lastly, add graph. This is very nice, very advanced, honestly. It's similar to what we are doing. It's more advanced because here it's used temporal graph neural network, and our is not temporal. So it can even capture more advanced patterns. And it's semi-supervised. Our is completely unsupervised. What I took from this paper, most importantly, is the edge-focused approach. So of course we are talking about the graph, and we have nodes and we have edges. The nodes are the devices and the edges are the connection. Mostly the graph neural network, they just work with node data. So for example, IP address, number of total packets, but they don't work with connection data. What I try to integrate from this paper is this idea of edge-aware graph attention network. What is our architecture? So based on these data sources, more or less we already talked about this. We have Zik logs. Zik is a software for monitoring network traffic. It creates a lot of different files with different information, for example, about certificates, about protocols. We parse these files into the C++, that's called log2graph software in real time, and we construct this graph that then gets passed to the Python module. It's called graph monitor, and this Python module parses this graph. It creates an internal representation. It can also perform some visualization, and then it outputs like this kind of anomaly detection. So when it sees a behavior that is not common, it tries to output. We will see now more in detail how these two components works, and this will be all the presentation. So we will really try to deep down these components. So the graph builder is the C++ core. You can see on the right, it's like a kind of workflow. It's to simplify, because in reality all this thing is multi-threading, so it's happening in parallel, but these are the main components. So we have a log monitor, that is something that is constantly monitoring the logs and ingesting them. We have graph builder, that is something that takes care, all these things, of course, they are classes, so they are different objects that are instantiated to do this. The graph builder is a singleton object that takes care of constructing this graph based on the log. Then we have the class to represent the graph, that is made of nodes, and here it says aggregated graph edges. Why aggregated? Because the connections are so many that we cannot have one edge per connection. think about, you open Google, you type something and it's already like 10 connections maybe. So they are aggregated based on 5 factors, like the source and IP, the source and destination IP address, and the source and destination port, and the protocol. So this is why I say aggregated. And then we have the graph exporter. So it's simply a class that takes care of taking this in-memory representation that we built and exporting them. There are many classes apart from this. I will cite one more that I didn't have space for, is the encoder class. Because since we are talking about feature engineering at this stage, we need to encode feature, and of course I'm talking about the technical aspect here, but a very important aspect is the feature engineering. We will discuss it more later on. But what took most of the time in developing this component is not the technical side, but is more like the identifying which feature are beneficial for doing attack anomaly detection. Then we have the graph monitor. Here we will really dive in because it's the main part of the project. Of course, we have some core modules, the entry point for the program, the main file. We have a file that defines the workflow, so how the program is supposed to work. And you can see on the right we have 2 operating modes. So of course it's a machine learning, so it needs to learn first and then it can detect. And then we have a file with all the neural network logic, and the file, very important to, for example, visualize how the model is representing devices. This is a topic that I would have loved to have more time to explore. At the end, I didn't put it in the report because there was not enough time. But for example, you can really kind of walk in the shoes of the model to see how it sees the network. For example, you can visualize how it learns which feature does it use to distinguish between different kind of devices. And it's really important to have a feedback loop. So you try to do some detection, you try to see how it went, and most importantly why, and then you try to improve the model. This part we did a bit with Koi, very quickly, again, because 2 months it's not a long time, but it's very important to underline this evaluation part. How does a graph attention network work? So just a small refresher about neural networks. So they are a set of layers, and each layer is kind of, it says that it's made of neurons, because at the end it's trying to recreate how the brain works. And we have, for example, traditional neural networks that are very useful, for example, for image detection, for trying to do pattern recognition, for trying to, for example, even the LLMs, large language models, they are traditional neural networks. Why traditional? Because the distance between things is Euclidean. So, for example, if you think about an image, each pixel has the same distance between each other. And with graph is not the same, because maybe two devices are very far apart from each other in terms of, not in terms of physical distance, but in terms of similarity and maybe in the network, in the IP range. So it gets a bit trickier. It's not like looking at the network, is not like looking at an image where everything is the same distance. And why we are using graph attention network specifically, that are a subset of graph neural network, because of the attention mechanism. What does it mean? That, for example, if a device is connected to many other devices, of course maybe some are more important than others. For example, based on a lot of factors, not just on for example, on the frequency of the communication. You can have some devices that are more influential in how the embeddings are generated, so to say. And the attention mechanism, we will dive a bit deeper into this, is crucial to create this attention, so to discriminate between very useful feature and devices and not so useful ones. In practice, of course, this makes a huge difference between a traditional neural network and a graph attention network. On the right, more or less, you can see how in general the encoding autoencoder architecture works. So in this case, for example, the input features will be the nodes feature, for example, IP address, number of packets, protocols. The encoder, it's something that take all these feature and kind of combine them in a way, of course, with the learned weight and something like this. It combines them into an embedding space. So it generates for each node an embedding. And crucially, the embedding, it doesn't just incorporate node info, but also edge ones. So it's what we talk about edge aware. And then it decodes it. So how does it, to keep this in mind, we will talk more about this later, but keep this in mind. So there is this encode, you are into embedding space, and then you decode. This process is kind of like trying to summarize a whole article into like 10 words, and then from that 10 words you have to try to rewrite again the article. And this is crucial for how the detection is performed. So how does it work, this network? We have it's called Node Graph Neural Network Anomaly Detector. It's the module that performs this. And more or less what we said, so this is a gut encoder. They found something that takes the feature and create an embedding. Diving a bit in, so this is multi-head attention. So what does it mean? That, as we said, there are some nodes that are more important than others, and the number of heads is like the number of people that are trying to understand who is more important. And in practice, what does it mean? It means that it's very sensitive to a lot of different patterns with a lot of different features. So it's again something that in practice makes sense to do. And the embeddings, they are The embeddings, they are in 32 dimensions, and the network is of course is multi-layer. The number of layers is parameter, but I think the last setup has 4 layers, and so we take the node feature, we pass it to 3 or 4 layers, and then we generate the embeddings. These embeddings then they get used for 2 things. So this is the second point of this list: dual pathway detection. How do we know if something is anomalous or not? First, we have reconstruction error. So for example, as we said, we create the embeddings. So we are trying to summarize the article into 10 words, and then and this is the encoding, and then we do the decoding. So we try to rewrite the same article again from these 10 words that are the summary. If there is a high error of reconstruction, and this is the first point of detection. So if there is a high loss in trying to reconstruct the node, we know it's something anomalous. So this is the reconstruction decoder, and then we have anomaly scoring MLP. This is a bit more tricky because this component is directly looking at the embedding as a number, because at the end the embedding is a vector of we said 32 dimensions. It's trying to take this vector, make it into a number, and just say if it looks kind of weird. There's nothing more to it, so it's just kind of basic pattern recognition. It should use a very complex architecture. We didn't get yet to the point where this actually works, but it's very interesting. Because it just uses one number, so it's very powerful in what you could achieve with this. In practice, it, of course, is a bit tricky to create a network that is so complex that it can understand just by looking at one number. We have an online learning framework. This is crucial because, as I said, the system, it works in detect and in train mode. But in the real world, the network is every day is evolving. So you need to have some kind of online learning. What does it mean? That even when the network is in detect mode, it still is monitoring what is happening and is updating the model. There is a possibility to do this with something called replay buffer also. That a replay buffer is like an array, let's say a memory of past attacks, of past experiences, to avoid something is called catastrophic forgetting. So all this online learning, it's a way of keeping what is again, keeping what you don't have to forget accessible, and to keep updating your network as the time passes. The last point is like combined decision rule. It means that we take both the reconstruction error, what I say about the article and trying to rewrite it, and this anomaly scoring MLP, that is this complex network. And when you score an anomaly, it's when you signal an anomaly, you take the union of these two. Again, this is a very interesting, very powerful concept because it maintains a lot of explainability, but 2 months is not a long time, so the architecture is there, but this is all I can say for now, not much more. Just to look at the attention coefficient, so as we said, the attention is like the weight you give to the nodes in the graph. There are some weights that are more important than others. This look maybe like a bit scary, but it's very easy. What does it mean? So the attention coefficient for between two nodes I and J, it's calculated. First you look at the orange, so you project the node feature and the edge feature according to a weight matrix. So VW is a weight matrix, that is what the model actually learns with the training. And HI, HJ, they are the hidden states. Basically, for now we can simplify and say we are the node feature, and EJ, they are the edge feature between these two things. So how the node attention is calculated is you kind of concatenate these. You have an attention vector, and this is also something that is learned. So it's kind of selecting which parts of all these concatenated features are important. Then you have a activation function, and of course it has to be non-linear, so the leaky rectified linear unit. It's a bit technical. This specific function is because we want to avoid the problem of dying gradients. Since we are talking about deep learning, we are talking about simulating neurons like the brain, so we want still to have a kind of a consistent signal flowing from these neurons. And all this, it's with this exponential function that is just used to normalize the value so that the sum of the network is 1. I don't want to explain this too much. I just wanted to show you, so more or less we can see practically what we are talking about. Is all linear algebra, and what is really the learning here is learning this W and this A matrix. Dropping up, so this is the feature engineering. I will wrap up because of the time, but this is very important. So how do we represent this graph, this network? We have for node feature, we have behavioral features. So again, like ratios of outgoing, incoming, connection, protocol diversity. So of course, if your server uses always one or two protocols and then you see a surge, it means that something is weird. Something related to ports. So for example, how many privileged ports, how many different ports are used, and traffic volume, also very important. For example, when you have a DOS attack, the traffic volume go up very quickly. For the connection, again, they are aggregated, and each set of connection have some traffic statistics. So again, for the volume, it has some metadata, so like protocol service, and this is already rich feature set, but so much more can be done in terms of implementing more feature and trying to, maybe if the feature is not significant, trying to remove it. This is one last thing about online learning, so I will go very quickly over this. We already talked about experience replay, so to avoid catastrophic forgetting. Statistical monitoring is important because since this is a model, we want numerical stability to avoid inconsistent behavior, and we use Welford algorithm for this. It's to calculate running mean and standard deviation, but I will not focus on this. Adaptive learning rate is very important because it can help make the loss converge faster, What does it mean? It just means that since we are doing gradient descent basically, so we are trying to find the local minimum of a function, sometimes we change the step size to avoid getting stuck in a point and maybe kind of seeing the whole plot of the function, so to say. So it's very important. Again, train and detect mode, they are crucial because you cannot detect without training. We already talked about this. Most importantly, the reconstruction error, it uses a statistical method based on Gaussian modeling to try to discern anomalies from normal patterns. And this MLP, again, it doesn't work very well, but it's a fixed threshold, so it's a probability that the system outputs. If it's more than 0.8, it's they flagged like an anomaly. Interpretability. And to wrap up, again, I know I'm a bit over time. It's what is good about this project, what is good about this innovation, this technical innovation, is we use C++ for high-speed parsing, so both for memory and for CPU times, it's the best way to do this. We use the Python because all the machine learning innovation is there. There is no the equivalent. There is not the equivalent of PyTorch geometric. That is the library we used for graph neural network on C++. So we took the best out of the both world. What is good about this is also that it's open source and it's ready to deploy. So you can just take this today, put it on your router, it will work. And again, it's behavioral based, so it can detect even 0 days. Very important. So what's next? Again, what we built, we already know. What the strengths are, we already know. What's next, and now this is quite part, is how do we evaluate this? How do we know if this is actually doing something or not? Then how can we deploy this in a real life architecture? How does it perform? And how can it integrate inside a pre-existing security framework, let's say infrastructure? So, for example, alerting and some kind of real-world intrusion detection system. I will wrap it up now. I will close. So if you have some questions, we can go ahead.
Yeah.
Thank you for the attention.
Thank you, Luca. So yes, be careful about the time, and same comment as I did with to Abderrahman, because after all, you have less time to discussion. So this is also, I understand that you have many things to present, but be careful of that. But I will take maybe two questions. One question is not fully clear for me. Is as you are, I think if you go to the previous slide or maybe the slide before, yeah, that one. So basically, you are building, not the next one, where you are building a graph that is dynamic in the sense that is evolving. So I don't know at which frequency the graph is evolving.
Okay.
But each time the graph is evolving, you need to send it to the detection system. So how is the connection between them? Because you need to have a state to do the evaluation. So how does it work? I don't see the dynamic aspect of it.
It's a very good question, very practical. So this is actually one of the next improvements if we want in the project, because right now, as you mentioned, what happens is the graph is dynamic, so it's snapshot, kind of a screenshot of the graph is taken the timing is a parameter. So for us, we choose between 30 seconds and 1 minute, so one snapshot per minute. It can go up, it can go down, depends on a lot of factors. And but the hard part is how to you send it from the C++ to the Python. I thought about this a lot. There are some high efficiency ways to do this, for example, through shared memory or to sockets. All this is very error prone and it takes a long time to develop. So for now, what we did is we saved the file from C++ and we read the file from Python. Of course, this introduces a overhead, but if you save, for example, one graph per minute or one graph every 5 minutes, it's not a big one, because most of the processing is in building the graph. So, for example, calculating the feature, encoding them, and then it's in the Python in training the network, performing calculations. So it can be overlooked, this overhead, but it's something sensitive. Yes, the answer is it gets saved every minute for now, and it gets saved as a file.
Okay, so basically, currently, what you are doing, you get a snapshot of a graph, then you pass it you send it to the attention mechanism, and then you get the decision. And then you get a new snapshot again in the detection system and a new evaluation. Is that the process you are doing? Okay, because one of the first slides you were giving a throughput which was I don't remember exactly, but
80 gigabytes
maybe
per
60 gigabit per second. So that's why I was wondering, because if you say 1 minute, you are not at 60 gigabit per second. So
no.
So,
again, but that is a bit of different metric. So it's like how much your system can process and still perform detection nearly in real time. Because I think, of course, you're right in the sense that you have this bottleneck, like you are kind of pushing everything every 5 minutes or 1 minute or so. But I think that metric, it's more about how memory efficient or CPU efficient is your system, because since we are running it on very
I understand what you mean. But as you say, it's a network. I mean, it's a specific kind of system, and but definitely this thing needs to be very well.
And actually, this choice was based upon one of the related work in the dynamic graph survey. It talks about the difference between discrete and continuous graphs, and also hybrid graphs. So in this case, it's hybrid because it's something that is truly continuous. So like the network is not quantized, like one device can connect at any point, but we are making it discrete. So we are taking one screenshot every 2 minutes or so, and this is a hybrid approach, and is actually the most, according to this paper, is actually the most helpful way of kind of capturing a lot of relationships.
Okay, Luca, and I don't know, I didn't have time to have a look at your report, but I think it would have been, so maybe it is in your report, but it would have been nice to see an example of a graph, just to have an idea, an illustration. It could have been nice in your presentation.
Yeah, I think there is the example of a graph file. I'm not sure, but I think there is one.
Yeah, because that's it, as you are mentioning, that it's a kind of specific graph where you are doing some merging, so it would have been nice just to have an illustration. But the presentation was very clear.
Thank you for the feedback.
Okay, thank you. So we move to Coy. Hello, Coy. Sorry, we are a little bit late.